So counting techniques and probability strategies, so combinations. So we've already looked at permutations, which is a counting technique where order matters. Okay, examples such as words, passwords, putting someone in a lineup who's first versus second versus third. Today we're looking at where order does not matter. A collection of chosen objects for which order does not matter. So not. So combinations is another counting technique. It's written similar to a permutation. Okay, there's an extra type of, I guess, writing. So there's C with the brackets N, comma R, or NCR, or you'll see it in a bracket with the N on the top and the R in the bottom. It's not a fraction. There's no line in between it. That's also, when you see this always indicates a combination. And this we read as N choose R. Okay. The formula is a little different. It goes in line with, that's kind of an extension of the permutations. You'll see N factorial over N minus R factorial, which is that part is the same as permutation, but then we're also dividing out R factorial. It represents a number of combinations possible in which R objects are selected from N different objects. So first I'll just go through the different possible with the formula, show you guys what it means. So here we're choosing 8. From 8 we're choosing 5. So the formula for this would be 8 factorial over 8 minus 5, which is we're familiar to from permutations, but now we're also dividing out 5 factorial. This is 8 factorial over 3 factorial and 5 factorial. Okay. There's many different ways to get to the answer. If you need, you can multiply it all out, 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And do the same with the bottom. See what cancels out and then multiply. You should also have a factorial function on your calculators. Okay. If we were to calculate this, we get 56. You're going to see that the numbers are not as large as a permutation because we don't care about the order. We're just trying to see how many ways we can select 5 people or 5 objects from 8. Doesn't matter if that object was collected first versus second versus third. Just a matter of how many 5 objects can I select at a time. So there's 56 different possibilities. So if you think about the logic for B, 4 choose 4. How many ways can I select 4 from 4? One. If I have 4 objects, so let's say 4 people, and I need to select 4, I don't care about the order I've selected them. There's only one way I can select them, which is all 4 of them. Okay. And if you look at the formula, it works out the same way. The formula is 4 factorial over 4 minus 4 factorial over 4 factorial. So 4 factorial over 0 factorial and 4 factorial. What's 0 factorial? 1. So there was a note about that in our previous class. So 4 factorial divided by 4 factorial is still going to be 1, which the logic came up with the same answer. Same idea here. So we have 4 choose 0. How many ways can I choose 0 objects? 1. I just don't choose any. So, and if you look at the formula, it works out to the same thing. How many different hands of 13 cards can be dealt from an ordinary deck of 52 cards? Distinct cards. So you're going to see a lot of questions that have to do with cards, have to do with combinations. And so when you're playing with cards, you're usually dealt a number of cards. It's just a matter of holding the cards, having those 13 cards in your hand. It doesn't matter which order you got dealt them in certain games or certain scenarios. Okay. So if you're getting all 13 at once, okay, it's not a permutation. It doesn't matter which of the 13 I got first. It's just a matter that I have those 13 cards in my hand. So you're looking at how many different possibilities there are of having, how many different 13 card possibilities you have. Okay, so that's 52, choose 13. You'll see that I'll use this notation quite a bit. Doesn't mean that it's the only notation you can use. You saw there's 3 different notations. And the answer is quite large. So here order is important. Sorry, it's not important. I didn't see. If I did this as a permutation, you'll see even more of a difference. So let's say order was important. Just want to show you the difference in the numbers. So we don't write permutations the way we write combinations. So just look at, this is 6.3 times 10 to the 11. It's 10 to the 11 as opposed to 3.95 times 10 to the 21. So quite a difference. Example 3, from a group of 5 women and 7 men, how many committees of 4 can be formed with 4 women? So now we're just forming committees. There's no roles in these. It's just a matter of being selected for the committees. Okay. So again, whether or not you were selected first or second or third or fourth doesn't matter. It's just a matter of being on the committee. So the order is not important. So we're talking for A, we're talking about 4 women. We can only choose a woman from a woman. Okay. So how many women do I have to choose from? 5, and I need to select 4. So I have 5 women to choose from. So I do 5, choose 4, and my answer is 5. If I look at men, the 4 men, I can only choose a man from a man. So I have 7 men to choose from. 7 men, sorry. And I just select 4. And 7 choose 4 is 35. Three women and 1 man. Okay, so let me just start with the women. So we have 3 women, and we're selecting them from 5 people. And the men we have 7 of, and I need only 1. What do I do with an and? What's the operation I'm going to do in between that to get both? What's a multiplicative law? What do you think? Multiply, yeah. Okay, so we're looking at 3 women and 1 man. So we're going to find out each number of possibilities, and then we're going to multiply. So we're going to use the multiplicative law. So we're talking about 10 times 7. So recall, and represents multiplying according. How'd I get the 10?
Yes.
So if I do 5, choose 3, you can either use the formula that I just showed you. So the 5 factorial over 5 minus 3 factorial times 3 factorial.
Oh.
Or, like I said, a lot of the times we're just using technology, which is our calculator in this case, that does that formula and gives you your 10.
Yeah, no, using the money.
So you can use your factorials as well, right? So the 2 women and 2 men, so I'm going to do 5, choose 2, times 7, choose 2. So 10 times 21. If you just look at 5, choose 3 versus 5, choose 2, you're going to notice this pattern as you go along, that 2 is what's left over from 5. Those will always be the same number. So anything with the remaining of the total will always have the same value. So just start paying attention to that while you do your work. No restrictions means that I'm not being biased and saying I need this many men or this many women. Just a matter of how many people I want on the committee. So I still need 4, and I have 12 people to choose from. So I'm just going to do 12, choose 4. I'm going to do example 5 and then come back to 4. A roster of 11 individuals is available for a basketball team of 5 members. One of those is Slim Duncan. In how many ways can the team be chosen without restriction? So that's A. So I have 11 members. I need to choose 5. So there's no restrictions. So I'm going to do 11, choose 5. Again, you can write it like this as well, or like this, whichever one you prefer. They're all acceptable. Oops, that's the same. Let me try it like this. Okay, those are 3 different ways of writing the same thing, and it's equal to 462. How many ways can the team be chosen if Slim must be a member? Okay, if he's already a member, he's already there, so you're not going to include him in your selection. You're just placing him there. He's no longer part of the choosing process. You're only selecting now from 10 people, and you only need 4 because 1 is already given. So you're removing him from the equation because he's a given member. You can think of him as 1, choose 1. Okay. So you can either just do like this and choose 4. So there's 210 different ways. Or if you're not seeing where he went, Slim, there's only one of him, and you have to choose him, and then you have to choose, so the multiplicative principle, 10 choose 4. We'll get the same answer, because 1 choose 1 is 1. Remember, and multiplicative principle. And then we have, in how many ways can the team be chosen if Slim is not a member? So now we're just still choosing from 10 because I'm not allowed to select him, but I need 5 people. So he's been, I guess, benched or kicked off the team. Okay, example 4 has to do with card games. So you might not specifically see questions on your test, in my class at least, dealing with these types of questions. So don't go learning how to play poker or anything. But you'll see similar type of questions with situations that you should be familiar with. Okay. But we will go through these probabilities to show you how awful your probability, your chances are, in hopes to deter you from gambling. Okay. So 5 cards are dealt at random from a deck of 52 playing cards. Determine the probability that you will have the ace, 2, 3, 4, 5 of the same suits. They call this a straight flush. Okay, so I'm looking for the probability of a straight flush. Again, I like to start with the denominator because that's where we're not restricting anything. I'm just going to look at being dealt cards. So I have 52 cards in a deck, my standard deck, and I'm being dealt how many? 5. So how many different possibilities are there to get 5? So I go 52, choose 5. This is no restrictions. My numerator, I'm going to put the actual scenario there. How many suits do I have? That's my denominator? Yeah, but I'm going through my numerator now. How many suits do I have? In a deck of cards, I have hearts, diamonds, spades, clubs. Well, right? There's 4 suits. Okay, same suit, so I need one of those same suits. So there's 4 suits, and I need one of that suit. So that's 4, choose 1. And I specifically need of that suit in the 4, I will need the ace 2, 3, 4, 5. Well, in each suit, there's only one of those. So just 1, choose 1. And because I want the same suits and so this is just, in every suit, there's only one ace 2, 3, 4, 5. I'm going to have to select 1 from the 1. So multiply all this and divide it. Try and do it in one shot and tell me what you get. Just going to write the final value down. This is the percentage I've written down. So not a good chance of getting that. And my probability is 0.00153%. So just logically, in B, we're talking about any straight flush. So 5 cards in a row of the same suit. Should my odds be better or worse? Matthew, what do you think? Should my odds for B be better or worse? Better, because I'm not restricted just to ace 2, 3, 4, 5. It could be 2, 3, 4, 5, 6, 3, 4, 5, 6, 7, 4, 5, 6, 7, 8. It keeps going. Okay. So the probability of any straight flush again, my denominator has no restrictions, so it's still a matter of how many ways can I be dealt 5 cards from 52. But my numerator is what I'm looking for. So I'm looking for any straight flush. So again, same suit. So there's still 4 suits in a deck of cards. And I need any one of those. And so the intersection, I need one of something. How many possibilities are there to go 5 cards in a row? Try and count them in your head. Ace 2, 3, 4, 5, 2, 3, 4, 5, 6. So if you count all five cards in a row, you'll get 10 possibilities. So there's 10 different 5 card in a row possibilities to choose from. I only need one of those to actually get my straight flush. So my odds are a little better. My probability of getting a straight flush, but not that much better. 1 second. Was